All right, we're starting the year, and I want to start with some simple things you should have studied for some polyatomic ions and your solubility rules, and now you're going to get some information on how to make it easier to memorize all of these. So here's a bunch of little tidbits for you. Um, so if fluorine, chlorine, bromine, or iodine, those are the halogens in the periodic table. There's another one, but just for these. If any of these are in a polyatomic ion, the charge of the polyatomic ion is going to be -1. So for selenium, charge will be -2, phosphorus, charge will be -3. Now this is interesting because if you look at a periodic table, by the way, this is where this site is, this website. If you look at a periodic table, this column right here, I'm hoping you remember, this is the -1 column. When these are ions by themselves, monatomic, they have a -1 charge. These are the -2s, -3s. So notice, -1 column all have a charge of -1. Sulfur and selenium are in the -2 column, right here. And phosphorus was in the -3 column. So the polyatomic ion charges actually match the charge for the monatomic ion when it's by itself, for most elements. Okay, that's what it says right here. But some exceptions are carbon and nitrogen. So for nitrate and nitrite, the charge is -1, but nitrogen's in the -3 column. For carbonate, carbon is in the +4 or -4 column, but the charge on carbonate is not -2. Notice, though, these are both in the second period, and the charge of the polyatomic ion is different from the charge of the element itself by 2. So second period, and the difference in the charges is 2. So -2 to -4, difference is 2. -1 to -3, difference is 2. Just a little way to memorize those things. Okay, now the names of the polyatomic ions, that was just how to memorize some of the charges, or not to memorize them, just use the periodic table to help you know them. The names of the polyatomic ions, well, we have a lot of eights and ites: nitrate, nitrite, phosphate, phosphite, sulfate, sulfite. When you have two possible different oxygens, the more oxygens you have, or the polyatomic ion with more oxygens will end in 8. The one with fewer oxygens will end in ite. Now, some polyatomic ions have 4 different possible oxygen atoms: 1, 2, 3, or 4. This would be everything in the halogens. So, well, not everything. They can't all have 4. But basically, we look at these as having 1, 2, 3, or 4 oxygens attached to one of these elements. And the way those get named is if you have 1 oxygen, it's hypo-root-ite. So if we just use chlorine as an example, ClO 1- would be hypochlorite, ClO2 would be chlorite, ClO3 1- would be chlorate, ClO4 1- would be perchlorate. And this works with chlorine, fluorine, bromine, iodine. So iodate would be this one. That means you have IO3 1-. Perbromate, so that would be bromine. Perbromate would have 4 oxygens. That would be Br for bromate, O4 1-. So just giving you an example here of perchlorate. All right, on to the strong acids. Probably heard this before. We sing this. We don't sing it. We just say it. Heber, Hickel, I, Hano, Hio, Hickolo, H2SO4. Changed it a little bit from prior years. So Heber, Hickel, Hi, Hano, Hio, Hickolo, H2SO4. Those are your 7 strong acids that we are going to care about in this class. And then just some hints. I'm not going to leave this up, but you can read through that. So why do we care about these strong acids? Why are they so important? They dissociate. They break apart completely into H+ and whatever other ions are in there. We don't care about the other ions so much. I mean, sometimes we do. They could be oxidizing agents. But for now, what we really care about if we're talking about acids, we care about the H+, the hydrogen ions. Those are the reactive center, the reactive part of an acid. That's for our purposes now. There are actually other kinds of acids. But what we care about is this H+. Well, if you split completely so that all the HBRs become H+ and Br-, you're a really strong acid because all of your H's are going to be present as H+. All other acids not included in this list right here are weak, and they only dissociate, ionize, break apart very little, less than 1%. Now these words, dissociate, ionize, break apart, interchangeable. We'll be using that vocabulary all throughout the year. Okay, now let's look at chapter 4. So, section 4.1 talks about water. Water is a very important substance. I'm hoping you memorize, or not memorized, but have remembered from your chemistry in the past that water is a very polar molecule. There's a little delta plus here. I'm going to make this bigger so you can see it better. Oop. We'll undo that in a moment. So water has a positive end where the hydrogens are and a negative end where the oxygen is. And it's a very polar molecule. It can do hydrogen bonding. And when ionic compounds that are soluble dissolve in water, the water molecules will surround those ions. So here we have a Na+, a sodium ion. So the water molecules surround the sodium ion in the water solution part, and the negative end of the water aligns with the positive sodium ions. And over here, this whole crystal is sodium chloride. So the chlorides are the big greens, and the sodiums are the smaller metal-colored balls. Chlorine is a green gas, that's why they're marked as green here. Okay, so the chlorides are negative ions. So which part of the water will align? The positive part. So you'll notice now the positives of the waters all align with the negative of the chlorine. This is called hydration. On to section 4.2. So this is about electrolyte solutions, and there's nothing really fancy about this. Electrolyte, this word gets students freaked out sometimes. You just think electrical. What does electricity do? When we turn on the electricity, lights light up. It means that there's electricity flowing. An electrolyte solution is just a solution where electricity can move through the solution. The solution can conduct electricity. So compounds that break into ions in water can cause the water to conduct electricity, and the compound's an electrolyte. The solution, when the water has dissolved ionic compounds in it, or things that produce ions in it, the solution of the water and the compound is called an electrolyte solution. The electrolyte, or the compound, is called a solute. The water is a solvent. And solutes are things that dissolve in solvents, and the solvent is always larger in mass quantity, not size, but has a larger total mass. So if I have 10 grams of one substance and 100 grams of another, the 100-gram substance is the solvent. Okay, strong electrolytes split completely. Weak electrolytes split only slightly, and weak electrolytes only conduct weakly. Strong electrolytes conduct completely. If a substance doesn't break into ions at all, it would be called a non-electrolyte. So here are some examples of strong, weak, and non-electrolytes. On to section 4.3, units for solutions. We use molarity. You should remember molarity from the past. It's a very simple equation. Molarity, which we denote as capital M, is moles per liter, moles solute per liter solution. Note, very important, it's not per liter of solvent, it's per liter of solution. And the solution is the mixture of the solute and the solvent together. All right, I want you to calculate the molarity of each ion in the following solutions. Now, you're not going to use this equation. This piece, I will do the first couple for you. The first one's really easy. Okay, so I've filled in this first one for you. So if you have 0.150 molar sodium chloride, you have 0.5 molar of both the sodium and the chloride ions. Now this one's a little trickier. I've written down the charges. You should be able to figure out the charges from the formulas here. But calcium is +2, it's in the +2 column. Chloride is -1. Now calcium You know, pause if you think you can do these on your own, and you can just go to the end when it's all filled in, and you'll see where you might need to change things. So, calcium, I only have one calcium in each of these, so the calcium will be 0.50 molar Ca2 plus, but the chloride ions, I have two chlorides in each one of these, so the molarity doubles. 5.5 molar calcium chloride, there's two Cl's in there, then I have 1 molar chloride. Now use that same model, recognizing cobalt should be the same. Nitrates, I should have 2 nitrates for every one of these things, so the molarity will double. And I'm going to fill in all the rest. So if you don't want to see everything, go ahead and pause. Otherwise, you're about to see the whole thing. All right, just one place where you might have gotten stuck. You probably got this one wrong. I was totally just putting a little trick in there because hydrofluoric acid is not one of our strong acids. And if it's not a strong, where are those strong acids? It's not one of these. And if it's not a strong acid, it's not splitting apart much at all. So the concentration is basically the original concentration. This will come up much later when we get into equilibrium problems. But even though a little bit of this splits apart, the concentration for our purposes stays the same. Now you might also be wondering about sig figs here. I kept 3. We only had 2 here. You know, in this class, it's okay to keep 1 extra or 1 too few sometimes, but we're just going to be more precise here. All right, because actually you could look at this as addition, and we really should go up to the hundredths place, because when you're multiplying, sometimes you're actually adding. Anyway, we'll go into that later. All right, diluting. So scientists, we keep these stock concentrated solutions in a chemical supply room. And these solutions, we use them to dilute to get some concentration that I need. So I might have 1 molar sitting in the lab, and I only need 1.1 molar for some lab that we're going to do. But I have 1 molar sitting there in the stock room in the laboratory, and I need to do a 10-fold dilution. So I'd use 100 mils of the stock solution, 900 mils of water. Now I'd have a 0.1 molar from my 1 molar. That was a lot of words. You don't need to write those down. So here's our equation. MiV is mfuf. I is initial, F is final, molarity, volume. So let's do a problem. We've got 1 molar H2SO4. We want to make 50 mils of 0.25. Notice we're diluting from 1 down to 0.25. I'm just going to go ahead and put those answers up. You can pause this. This should be pretty straightforward. All right, so we just identify our variables and then plug them into our equation. You'll notice I kept 3 sig figs here, even though there were 2 in each of these pieces. Well, if I have the equipment to be able to measure to tenths of milliliters, I might as well keep it to 12.5 instead of rounding this to 13 milliliters. When you're making your actual solutions, you want to be as cautious as possible in making the solutions. And yeah, okay, precipitation reactions. Moving on. You will notice that the solutions disappeared. That will happen, but you can always reverse if you need to look at them again. Okay, so precipitation reactions. This is a type of double displacement reaction. You might remember this from last year, but we're going to review it. So procedure's all written down. You can read through this at your own pleasure. At your leisure. With pleasure, I'm sure you would read through this as well, because it's so nice reading through directions on how to write net ionic equations. And I've rewritten your solubility rules for you here. And let's do an example problem now. So first we need to, what do we need to do? I'm back at another place. We put the cation for the first compound with the anion from the second compound, and the anion from the first with the cation from the second. We put cations on the left. Okay, so I've done the first step. You might be wondering, how did I get this formula here? Well, because they said lead 2, I know it's Pb2+, and nitrate, I know, is NO3 1-. So we get these formulas in the front just from knowing the charges. Sodium is in the +1, chloride -1, etc. Now, the next step, I have to determine the formula of the products by making the charges add to 0. +1, -1 is just going to be 1 to 1. Pb with 2+, Cl1-. How many Cl's am I going to need? 2, and the formulas become, voila, here are our formulas. Now we need to balance the overall equation, and this, you can do, pause, if you want to do this on. All right, now it's balanced, and now we will get the net ionic equation, solubility. Do this on your own, pause, but soluble, you don't even need to check these. If you're told you have a 1 molar solution, you know these things are soluble. Okay, all nitrate, this is soluble, this is insoluble. So our information says, write the solubility of all 4 substances. We've done that. Write the formula of all insoluble substances directly under the substance along with its coefficient. I'm going to do that now. You can do that on your own. Okay, that's done. This is the only insoluble substance. And then it says, identify which ions are missing or needed to balance the overall net ionic equation. Write these under their original compounds along with the correctly balanced coefficient. And you're done. So I look at this and I say, I need some lead. Well, here's the lead. So I'm going to put that underneath the lead. And I have to make sure I write the charge in there. And there was no coefficient. And look, 1 and 1. Very nice. And then I've also got some chlorines over here. Oh, I also need my arrow. Don't forget your arrow. I've got some chlorines over here, and I need them from here. And these are Cl minuses. And I have 2 of them, according to this balanced equation up at the top. There's the coefficient. And the direction said, use the coefficient. So here we go, and it is balanced, and we are done. Okay, do this on your own. I'm about to show you the answer, so make sure you pause. Pause this, because the answer is showing up momentarily, so pause. Okay, here is my molecular equation, or my reaction, the overall reaction. I got these formulas from this right here, and sodium carbonate carbonate's -2. We have to make this all add up to 0. Make this all add up to 0. Now I put the iron with the carbonate. Iron was +3. Carbonate's -2. To make that add to 0, I need 2 irons. If I have 2 iron 3s, that adds to +6. Carbonates are -2, and 3 -2s is -6. So this did add to 0. Sodium's +1. Nitrate's -1. We're good. All right, now for the net ionic equation, and again, you can fast forward through this if you know how to do it. Net ionic equation, solutions are already soluble. I just leave them. I know they're not going to come down. This thing is insoluble. Carbonates are insoluble except with alkali metals and ammonium. Sodium nitrate, nitrates are always soluble. Sodium with other ions are always soluble. So now pause again. I'm going to show you the final answer. We're going to bring this iron 3 carbonate down, and then we'll need the irons and the carbonates. Oh, what? From the other side, but I need to balance this first. Sorry about the interruption there. Oh, we got to balance this first. I was realizing this wasn't balanced. So do I need 6 there? I think I might need 6. I don't know. I need 2 here. I need 3 here. No, it's way over here that I need 6. Okay, I'm going to pause. You should pause. Here comes the answers. There's your answer. All right. I'm going to wait on stoichiometry because that's a really long section. So that's it for now.